All right, so some of you all expressed that the video about chemical weathering was a bit confusing, so I'm going to do sort of a recap or a take two here. Again, we're talking about chemical weathering, which is this process of rocks basically being dissolved by rain, and how that process serves to draw down the global concentration of CO2 in Earth's atmosphere and ultimately cause global cooling. Okay, so just to recap this here, we've got sort of like a little cartoon of some mountains, the edge of a sea, a shallow sea area here, and then deep ocean off to the right-hand side. And so when we're talking about chemical weathering, we sort of have four steps that are going to be important in the process of carbon from its form as CO2 gas in the atmosphere to ultimately being preserved as limestone in the rock record. So the first step is that rain, H2O, mixes with carbon dioxide gas in the atmosphere. And that mixture makes this thing called carbonic acid. So H2O, rain, plus CO2 gas makes carbonic acid. Okay, that rain falls and lands on exposed rock. This is going to be it's going to happen in mountains, right, where there's bare rock. Okay, so that carbonic acid dissolves minerals. So minerals, of course, if we remember from the first part of the class, are what make up rocks, right? And so in this demonstration, we're doing a generalized example of a mineral called wollastonite being dissolved. But I want to note that basically all the different kinds of minerals out there all have their own dissolution reactions with carbonic acid or some other kind of acid, right? So all the different minerals that we've learned about can be dissolved by chemical weathering. We're only talking about one specific example here. So in the previous version, I sort of said that, I included just minerals in here, right? So I was trying to make the point that each kind of different mineral would have its own reaction. We're doing just one example. Okay, so carbonic acid is going to fall with rainwater onto exposed rock, and carbonic acid will react with that rock or that mineral. In this case, is the mineral wollastonite. Carbonic acid will dissolve this mineral wollastonite, and it'll release the calcium. It'll dissolve that, and it'll be released into runoff water just as a free cation. Remember, a cation is any positively charged element or molecule. So calcium is released, a molecule called bicarbonate is formed, and quartz is left over. So you can sort of see that calcium and SiO2, but there's a bonus oxygen there, right? So SiO3. Calcium is being removed from the mineral wollastonite, and what's left over is quartz. That calcium is liberated to be free and dissolved in runoff water, along with this molecule called bicarbonate. Okay, so those cations, calcium, and like I said, there's other minerals that get dissolved in this way. Calcium is just the one that's the cation that's important for this process. So cations like calcium and bicarbonate, HCO3, are washed into the ocean by rivers. Okay, so the rainwater dissolves the rock, and then that rainwater runs away in rivers and eventually makes its way to the ocean. And when it gets to the ocean, it's carrying calcium and bicarbonate with it. Okay, finally, once that water and those cations and that bicarbonate enter the sea, then it's available for sea critters to use to make their shells. So sea critters use calcium and bicarbonate. They extract that from ocean water to make shells out of calcite, the mineral calcite, CaCO3. Ultimately, those critters will die, and their shells get compacted and lithified and turned into the chemical sedimentary rock limestone, which is basically just nothing but calcite. Okay, so that chemical reaction is shown here, calcium plus two bicarbonates. is going to make limestone and then release some CO2 and some water. So that's sort of taking place here in shallow seas where limestone can form. So these 4 steps are all represented in this single balanced chemical equation. And what this is describing is the dissolution of rocks at the surface of the Earth and the consumption of atmospheric CO2, right, taking it out of the atmosphere, and then ultimately transporting that carbon into a shallow sea where it's turned into a new rock called limestone. And this process locks away carbon in new rocks that were made by dissolving old rocks by chemical weathering. Now, the important difference between this process and the burial of organic carbon made by photosynthesizing plants in the sea and from like dead fish and whatnot, the important difference between the burial of this carbon and storing that away in rocks and the burial of this carbon as limestone in shallow seas is where this action happens. So step 4 here, the deposition of limestone at the bottom of shallow seas. This takes place at the edges of continents. So I've sort of shown some mountains up here, the surface of the sea, a relatively shallow part of the sea, and then a drop off into really, really deep parts of the sea. So this is sort of a representative, curve of what the actual ocean floor looks like. And the reason for this change in the depth of the ocean is that the shallowest parts of the sea at the very edges of continents are in fact still underlain by continental lithosphere. So if you remember back to the first part of our class, talking about the different kinds of tectonic plates, the different kinds of lithosphere, we know that continental lithosphere is less dense than oceanic lithosphere, right? It's buoyant, it floats, and so that means that it's preserved for a very, very long time in the geologic record, right? In rocks. The rocks of continents stick around for hundreds of millions of years or even billions of years. But this organic carbon that gets buried on the deep ocean floor, this is deposited on oceanic lithosphere, right? And so we remember that oceanic lithosphere is more dense than continental lithosphere. It sinks or subducts, which means that this carbon that's buried down here is ultimately going to be recycled back into the mantle, by subduction. And this process happens continuously over geologic time. So this stuff that's deposited down here is very quickly returned, well, relatively quickly, it still takes millions of years, but continuously returned back to the mantle through subduction. This stuff can stick around for a really, really long time, billions of years, hundreds of millions of years. And so where our carbon gets deposited in the ocean is going to be a very important difference for determining how CO2 is pulled out of the atmosphere or pulled out of the organic reservoir and moved around in the Earth system. So this process, chemical weathering of rocks and formation of limestone in shallow seas, takes carbon dioxide out of the atmosphere and stores it in rocks. But this process of burial of organic carbon takes carbon from the oceans and from the biosphere and buries it in the deep ocean lithosphere, where it's returned to the mantle and ultimately put back into the atmosphere at volcanic epicenters, right, at volcanoes. So that's the really important difference. This process pulls CO2 out of the atmosphere, and that's important because CO2 is a greenhouse gas, right? So that has immediate effects on the Earth's climate. Pulls CO2 out of the atmosphere, cools the climate, whereas this process is mostly in balance. There's a constant supply of carbon going down, and there's a constant supply of carbon coming out from volcanoes. That can vary as well over long periods of time, but it's generally pretty balanced. So this stuff pulls it out of the atmosphere. Very important point. And then the other important point is that this takes place generally at high mountains. And starting 50 million years ago, very high mountains were made at the Tibetan Plateau, where India collided into Asia, starting about 50 million years ago, making lots of bare rock available for chemical weathering, causing a drawdown in atmospheric CO2 by chemical weathering and storing carbon as rock in the oceans, causing a long-term global cooling for the last 50 million years, which we see in the benthic foram record. Hope that clears things up for you and that you enjoyed this video.